So now we'll basically look at the periodic table and the property of elements.
Yep.
And let's take a look at the periodic table here. So a few very basic things to start. Your periodic table lists out all your elements in increasing atomic order, atomic number. So you can see from the top left, it's got basically hydrogen starting at number 1 and going across, got 2, 3, 4, 5, 6, 7, 8 to 10, and so on. You can see these numbers here refer to the atomic number.
Yeah.
Now, as we go across, each one across, this is called a crosser group. And we also have columns. So this is going down a group. So remember, a group is basically a column.
Is it across the period?
Yes, I should fix that. It is across a period, which is a row, and down a group, which is a column. Your periodic table separates things quite basically into your metals and non-metals. So you kind of have this approximate zigzag line, where we kind of sort of say that to the left of that are metals, and to the right of that are non-metals.
Yeah.
It's a slightly arbitrary line, but the point is we say metals form ionic bonds, and we'll talk about that very soon, and non-metals form covalent bonds and so on. And, you know, but it's not as clear-cut a line as I'm sure you know since we're sort of revising, because it depends on the electronegativity. Now, these are your periodic tables. Across is for a period, and down is down a group. And we should probably, at this point in time, although we say that, you know, it is arranged this way, we want to talk about why it's sort of arranged like this. Now, this is actually arranged in this shape because of electron configuration. So this here is the S block. This here is the P block. Technically, this one here is also the S block as well. It's kind of the exception, being over here. This is the P block. This here in the middle is the D block. Although there's a few exceptions there, but that's the D block. And at the bottom there is your F block. So basically, your periodic table is arranged in increasing atomic order, but why didn't they put it just in one row? Or why didn't they just go like, you know, why didn't they simply go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on? Is because of the fact that it's a periodic table. And the word periodic means that there is repetition or a cycle. And the point is that everything in group 1 has similar chemical, to some extent physical as well, but focusing on the chemical properties. So the groups are arranged in similar chemical properties. And that's why helium, despite being in an S block, is put here, because it's in a similar chemical properties to all the other noble gases, right? So you may want to be aware that group 1 is called your alkali metals. Group 2 is called your alkaline earth metals. The yellow parts are the ones in the middle are called your transition metals. You probably don't need to worry about these ones as much, but you do need to be aware of your non-metals, which, well, are these. Not halogens are also non-metals, and your noble gases are the ones on the right. And you've got your lanthanides and actinides at the bottom, but those, while used, probably won't be tested as much. So those are your different terms. Now we should probably explain your electron configuration a little bit. So let's take a look at that now. So your electron configuration is in terms of the fact that electrons are arranged firstly in shells. And once after they've arranged in shells, the next thing after that is they're arranged in subshells. And then within each subshell, they are then arranged within an orbital, a specific orbital within the subshell. And then within the subshell, then you've got the spin up or down. So your shells are what we call, like, you know, your first, second, third, fourth shell. Your subshells are kind of like your S, P, D, F sort of subshell, and your orbitals are kind of the orbital within the subshell. So your basic rules are simple. Each shell can only hold the same number of subshells as itself. So in fact, for example, shell 1 can only hold the 1s subshell.
Yeah.
Shell 2 can hold 2, so it can hold the 2s and the 2p. Shell 3 can hold the 3s, the 3p, and the 3d, and so on.
Yeah.
Now, each subshell can hold a certain number of orbitals. So subshell S can hold 1 orbital, subshell P can hold 3 orbitals, subshell D can hold 5 orbitals, and subshell F can hold 7 orbitals. And you can probably see the pattern here. It's just going up in the odd numbers. But each orbital can hold 2 electrons. So in terms of simplifying it, the number of electrons held would therefore be 2 electrons by the s orbital, 6 in total by the sort of subshell of the p, 10 for the d, and 14 of the f. So you guys aren't tested too much at the, you know, orbital to orbital level, like not specifically. So we'll just sort of kind of focus on the subshell. So just note that s can hold a maximum of 2 electrons. P, if you look at all the p orbitals together, can hold a maximum of 6. D can hold a maximum of 10. F can hold a maximum of 14.
Yeah.
What that then means then is your first shell has 1s only, so it can hold 2 electrons only. Your second shell is a 2s, then 2p, giving you 2 plus 6, which is 8. Your third shell is 4s, is 3s, 3p, and 3d, giving you a total of 2 plus 6 plus 10, which is 18.
Yeah.
Now we can go to the fourth shell and beyond. So we've got 4s, 4p, 4d, 4f, which will then be 32 total. The fifth shell has a 5s, 5p, 5d, 5f. There's also a 5g that's been theorized, but it really doesn't matter at this point. Your sixth shell is 6s, 6p, 6d, 6f, and theoretically there will be other subshells after that, but they don't really matter. And the point of the matter is that your electrons are going to be arranging themselves in terms of lowest energy first. So as a close approximation, without talking about the transition metals, that means you're going to have 1s followed by 2s, followed by 2p, followed by 3s, followed by 3p, followed by 4s, followed by 3d, followed by 4p, followed by 5s, followed by 4d, followed by 5s, 5p, 6s, okay, and then 4f, 5d, 6p, 7s, all right, and then 5f, 6d, 7p, 8s, and so on. And we get that by basically drawing 45-degree lines, going this way, and seeing which ones they intersect first. So that's why 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, 8s, and so on.
Yeah.
And going back here, you'll see why 1f is this 1s1 here, 1s2, and 2s1, 2s2, and so on. And so that's why, as we said earlier, this is your S block over here.
Yeah.
You'll notice that all the ones over here is going to be your P block. All the ones in the middle here will end in a D, so that's your D block. And then your lanthanides and actinides are going to be your F block.
Yeah.
Great. Now, we also have to talk about trends. So trends in the periodic table. We basically need to think of what happens as it goes down a group and across a period.
Yeah.
Now, down a group is probably easier. Basically, understand that every time you go down a group, you are increasing the number of shells. So as a result of that, and you will need to know how to explain it, but if you are going down a group, that means the atomic radius will increase.
Yeah.
Because after all, you're adding on a nitrous shell. As a result of an increase in atomic radii, then essentially your first ionization energy will go down because you're further away from the nucleus.
Well,
And similarly, because you're attracting the electron on the outer shell less, that means your electronegativity will also go down.
is first ionization energy like the energy for ionic bonding?
For forming a cation.
Okay.
First ionization energy is the amount of energy that you require to remove 1 mole of electrons from 1 mole of the substance in gaseous state, which basically means it's the energy required to form a cation,
Yeah.
form a +1 cation. So in other words, think of it like M gas to M plus E minus. That delta H is the first ionization energy.
Yeah. Okay.
All right.
Yeah.
And so your atomic radius increases, your first ionization energy decreases, your electron negativity in general decreases. And as a result, though, of these things, your metallic character increases, which therefore means for metals, you're more likely to react with water or anything. But as a result of that, your non-metals are less likely to react. Because it's the opposite, right? A metal normally reacts by giving away an electron, whereas a non-metal normally reacts by taking an electron. And as you go down, the more it wants to give it away. And that goes for metals and non-metals. But that means for a metal, it makes it more likely to react. But for a non-metal, that means it's less likely to react.
Yeah.
Now, if you want a shortcut, when you go across a period, it's going to be the opposite.
Yeah.
So when you go across a period, then atomic radius will go down.
Yeah.
Your first ionization energy will go up. Your electronegativity will go up. Before the noble gases anyway. Ignoring the metal gases, and your metallic character will go down.
Yeah.
You may also be asked to consider things like state at room temperature, which really relates to the boiling point and melting point. While you could force that into your sort of periodic table trends, I think that's much better to consider in terms of the bonds, and therefore their strengths, and that gives you, the boiling point or melting point. And so we'll discuss that then, which then gives you the states. But in simple terms, the boiling point would kind of increase and then decrease. So if you go across a period, then it would kind of increase and decrease. And as you go down a group, well, it would increase so it would decrease for a metal, but it would increase for a non-metal. And this is better explained when we actually talk about bonding, which is what we are doing next.